Yeah, Chip is going to be talking about returning treasure from the moon, fundamental importance of planetary sample return and fulfilling the scientific context for the exploration of the moon goals. Take it away, Chip.
Thank you, Clive. I just took my break.
Yeah, we know.
This talk was meant to be complementary to Clive's, focusing on the importance of sample return and trying to link it to the SCEM report and the updates and the evaluation of the SCEM report done recently and reported by Brett. Clive and I spent a lot of time coordinating these two talks, I think from 7:59 to 8 o'clock this morning. Thanks, Clive. What I'm going to do today is hopefully get through this in the time allowed, is really look at the planetary perspective from samples that are somewhat unique to other types of data we get on planetary bodies. Really focus a little bit upon the importance of integration of data sets, essentially integrating sample observations with remote observations, thereby for remote observations and orbital observations, providing ground truth, and for sample data that we get from a very localized site and could be on a very fine, small scale. The remote sensing data allows us to provide a planetary perspective for these sample data. Then I'd like to turn to sample return mission architectures in the simplest context, essentially looking at options that we have from fairly simple missions to much more complex missions and the technologies needed. And then finally, I'm going to try to go through some aspects of the SCEM report and again the recent updates and try to link sample return with fulfilling some of those goals. In terms of the planetary perspective that samples provide are illustrated here in terms of scale, precision, unlimited instrumentation, and a continuous mission. Some of us, such as Clive and myself, have been involved in the Apollo 17 mission for even now. So this Apollo 17 mission has continued for 45 years because of samples. The scale that one can look at is different from remotely sensed data in terms of this is just an image of some sheet silicates within a carbonate. And again, the scale that we're looking at here is 10 nanometers. We can't do that remotely. Also, the precision that one can derive from Earth-based instrumentation is exquisitely precise. Not only is the instrumentation, the measurements highly precise and can be accurate, but there is also substantial sample data and integrate them. So one can take isotope data, observations tied to petrography, petrology, mineralogy, and integrate those to provide a much fuller, richer picture of those samples. And then finally, as I mentioned, a continuous mission, unlimited instrumentation, unlimited due to size and power. Just as an example shown, whoops. Oh. Oh, I'm sorry. Oh, I'm sorry. Yeah. And this is the case. This is a beamline from Argonne National Labs, which is hundreds of meters across here. And so one can't put this on a spacecraft or its capability on a spacecraft, but if one has those samples on Earth, one can do these types of measurements. In addition, one can answer questions that one didn't even think of once those samples are back. and you can have multiple generations over decades answering new questions and utilizing new instrumentation. Sample return also is value added, and there are some investments that need to be made. As I mentioned, samples essentially allow one to provide ground truth for orbital missions, perhaps ground truth for in situ missions. And there are a lot of shared technologies between sample return missions and other landed missions that don't return samples and orbital missions, that they all benefit one another. Also, the sorts of requirements for sample return missions is there, of course, needs to be an investment in curation, probably beyond what we have down in Houston now, in terms of being able to handle fairly fragile samples, volatile-rich samples that we need to unlock their secrets. Also, there needs to be investments in laboratory instrumentation, and I know Jim currently has a National Academy review of trying to better understand what sort of instrumentation do we need for sample return missions. And this is not only investment just in instrumentation, but also an investment in people and generations. Also, there needs to be investments in sample return technologies from fairly simple to fairly complex. We haven't landed a robotic mission on the surface of the moon. The U.S. has never, NASA has never. So there may be investments we need to make there. And again, as earlier talks had mentioned, there needs to be maybe investments in collection of samples, preservation of samples if we're collecting volatile material. And then finally, one always needs, as Clive had pointed out in numerous other missions, one needs precursor missions for putting these samples within a planetary context. And right now we have that in LRO, that one can identify sites not only for their science content, but also for safety. There are sample return issues, which I mentioned this, outlined some of them here. And Jack had mentioned this earlier. What really is the trade-off between doing in situ analyses versus sample return? If one is going and trying to sample materials that are in their lunar environment, one would probably want to, in sample return, may disturb that lunar environment, to disturb the sample. It is probably better to initially do some in situ measurements and then perhaps return the sample, so one has a feeling for what one potentially lost in those samples. Also, the question, what do we need to know about the sampling location? Another comment that I wanted to make is very commonly sample return is thought to be the most complex mission, and therefore after we do orbital data, landed data, or collect landed data and run other sorts of missions, then as the crowning achievement at the end, you do sample return. I think that's a false architecture, and I think what one needs to do is constantly integrate orbital data, remote sensing orbital data, in situ data, and sample return data from fairly simple missions to increasingly more complex missions that ask increasingly more complex questions. And then finally, what is the trade-off between sample and complex sample return missions? And I'll discuss that a little bit later. This just illustrates at least some of the potential differences between simple or not very costly versus complex sample return missions. And I just list mobility, sample collection and preservation, and how we return samples to Earth. With regards to mobility, I think there are numerous scientific questions that can be answered with sample return, which essentially involves only a static lander. I think Brad's South Pole Aitken Basin, if one is looking for the cost-effective way of returning samples, can be done with a static lander. Of course, there are other missions that one may need rovers and mobility. Again, cost is a factor, safety is a factor, and the scientific questions that you're asking are important. Sample collection and preservation, there's simple sample collection and preservation, in which in some cases we did in Apollo, that we had a rock box that samples went into, and there was attention to cleanliness and trying to return materials without contamination. But clearly in this type of sample return, there could be a loss of volatiles, there could be an alteration of material, such as 66095, the rusty rock, which I've been debating with numerous people on the origin of that rust. Is it terrestrial? Is it lunar in origin? Also, the complex collection and preservation of samples, again, was done on Apollo, and that's kind of a lesson we can learn. And this is just an example of one of these sealed containers with the special environmental sample container that was, we still have a sample of this from Apollo 15 and curation. And of course, there is also the core samples from 16 and Apollo 17. In terms of return to Earth, one can have a direct-to-Earth launch. This may require a larger mass to put on the lunar surface, and perhaps being able to rendezvous in lunar orbit may be an alternative to put down a smaller mass on the surface. And this could be to an orbiting satellite that may also double as a communication satellite, or it could be gateway. Now let's go ahead and put these in terms of context with the exploration of the moon, the SCEM report, and advancing science of the moon that was accomplished in our workshop in December. Of course, I can't go through every concept that was discussed in both documents. And in the abstract, I cover these concepts in terms of understanding the bombardment history. Okay. The structure and composition of the lunar interior, key planetary processes tied to diversity of lunar rocks, lunar volcanism, the moon as a natural lab, and also lunar concepts from 2018, the water and the volatile cycle. And I've taken the subset of these and divided these into concept number in the SCEM report, scientific rationale, sampling material, targets, and sample return architecture. In this case, the understanding concept one, the bombardment history of the inner solar system, is uniquely revealed on the moon. One can return samples to determine their age from the SPA basin and other large basins to constrain models for impact bombardment of the moon and the dynamics of the outer solar system. Type of material that one could use is impact melt by, for example, produced by the SPA event. And as Brad mentioned, targets could be the interior of the SPA basin, the perimeter, or even adjacent to the SPA basin. And one, in terms of a sample return architecture, one can accomplish this, I think, with a static lander, perhaps sieve the regolith, and also relatively simple sample containment. The concept 5, lunar volcanism, provides a window into the thermal and compositional evolution of the moon. There are a wide range of sites that one can sample with regards to smooth plains and SPA, a variety of basins, and essentially sampling a wide range of basaltic materials in terms of age, potential age, composition, that will provide us with a better understanding of the thermal history and composition of the lunar interior. Remember, basalts are probes of of planetary interiors. And one could do this with a static lander, with mobility. the capability to sieve samples, but again, one could essentially have simple sample containment, but I think a program with a rover and some mobility would be very helpful. And then finally, the last concept that I'd like to discuss, and this is the new lunar concept that Brett mentioned, and that's understanding the water and volatile cycle. And this is really to determine the interaction and evolution of different volatile reservoirs on the moon, the interior, and the surface. This can be polar regolith, pyroclastic deposits, recently degassed deposits, and the samples are collected from the surface environment. It may be in certain situations that one does in situ measurements before sample collection. And of course, this architecture is much more complex and requires a much more complex sample containment, probably along the lines of the sealed containers on Apollo. Finally, in summary, as I mentioned here, sample return often offers a distinct planetary perspective, but is most powerful when it's integrated with other observations, like remotely sensed data and also in situ data. There are many, as Clive pointed out, and will be pointed out further along in the workshop, there are many well-documented high-risk sites to do sample return. And the sample return missions have a variety of complexity, from fairly simple to fairly complex in terms of containment, in terms of processing material on the surface, in terms of in situ instrumentation, in terms of a CONSAT. And then finally, there are technology investments that we have to make. Thank you.
Questions for Chip? Dean.
If you're constrained to a single lunar day, and you're constrained to the present speed that robots move on at least Mars, you're probably not going to get far enough away from your lander to get a sample that's different lithologically and then get back to your lander and offload it before the sun goes down.
I think you're right. And again, the advantage for a static lander, for example, on something like Moonrise, we anticipated functioning on the surface of the moon for on the order of, but for a lunar day, and landing in the morning and leaving in the evening. Yes?
Are you taking it?
Oh, go ahead.
Fred Borez, ASMS Incorporated. You touched upon some of the benefits of sample return versus in situ testing. In your opinion, would it be desirable to have such a module on Earth, on Moon, so that you can do all the in-testing right up there as opposed to bringing the samples down to Earth? The comment was made earlier that when you bring the samples, you have to worry about preservation of the samples as well as being exposed to the air environment.
You know, I think that has to do a lot with the science that a mission is going to accomplish. And that I had mentioned here that something like a science question that doesn't need to preserve some fragile component in the sample being collected, I don't think you need to do in situ measurements, although perhaps it would be helpful. But again, that would be also time consuming. With regards to much more complex missions that one wants to sample volatile reservoirs or some other characteristic of the lunar regolith that again is very fragile, one may want to do in situ measurements, perhaps then followed by sample return.
Thank you.
All right, I don't want to cut the question short, so these are the last three quick questions. Carl, don't monologue us.
Quick, thanks for the pressure. Right, Chip, agree with you with the need for conducting laboratory measurements on the return samples, and in particular I want to focus on volatiles, something I know a little bit about. And curating them is very important, as we know. Okay, so I would argue that any curation we have currently of the samples will be contaminated because it takes so little to affect the very surface that is implanted by the hydrogen. So that's something we have to look into greatly. Secondly, one should also look...
Just a comment on that, if I
Yes.
may. No, I think you're right. I think there needs to be technology and people thinking about how one could potentially preserve those very delicate features, not only during curation, but also during collection. And that could potentially even be a problem with in situ measurements. Do in situ measurements
agreed.
disturb those really fragile characteristics?
And to some extent they will, and one has to understand the phenomenology of it, the physics of it. For instance, if you want to understand...
You dropped out. You dropped out.
Yeah,
Could
you're
you?
done. Move on.
The other thing is, can one extract water from these samples? One should look, potentially conduct laboratory measurements of analogs to investigate some of these phenomena, and not simply look at lunar samples themselves, because analogs you can control, lunar samples are very complex.
One can do that, but also remember we do have sealed Apollo samples. That there are core samples.
You mentioned precursor missions, and I wanted to be sure everyone was aware that modern X-ray telescopes can give you few kilometer resolution and give you elemental abundances for of order a dozen elements.
Okay.
Over 100 kilometer scale regions. And I just happen to have a poster of opportunity to put up.
And again, what's really important is being able to take samples which give you one scale and place them in a much larger planetary context. That's right.
Pete Humphreys, ASMS Inc. I'm following up with my colleague here. I've had inquiries from biotech people, and there is a concern that when they bring some of the bio things back, I'm not a biotech person, just an engineer, that the contamination would occur. That's why they've inquired with us about in situ habitation units. So we got a presentation later on. Okay,
Okay,
thank
great.
you.
Thanks.